Okay, we'll kick off the afternoon session with the track on system support for AI. And the track is orchestrated by a very dear friend of MSR India, though he's no longer with us here in India, Chandu Tekat. Chandu was, in fact, managing director of MSR India before Sriram took over from him. And since then, he's moved now to Redmond. But he still continues to be a great friend of the lab. Chandu is, it's too long to read all his achievement, but I'll just quickly summarize. He's a distinguishing engineer at Microsoft, and he began his career in Microsoft at the turn of the century, so almost 20 years now. And he's worked across multiple areas, and I let Chandu do the talking for himself because he doesn't like too long introductions. And it's my pleasure to invite Chandu to kick off the afternoon track on systems.
The only thing I want to tell you about myself is that the last time I gave a talk at IIT Madras, I was a fifth-year undergraduate in electronics, and that was in 1982. So it's a great pleasure to be back and talk to you guys. We didn't have fancy auditoriums those days, except for the CLT. All right. So this session was advertised. This session was advertised as a panel discussion. It's not going to be a panel discussion. We're just going to run it like a regular conference track. I'll give you a brief introduction with a few slides on to motivate the track. And then we'll have three speakers who will each give you a full-blown technical talk as you would hear in a conference. They'll talk for 25 minutes, and then there'll be Q&A in the end to the speaker. All set? Good. Now let me see if I can get this to move. All right. So if you look at the history of AI by doing the admittedly crude procedure of typing a query into Google, and you look for something like deep learning as a proxy for machine learning and AI, you'll notice that there is a knee there sometime past 2011, maybe 2014 or so. And prior to 2004, it was pretty much non-existent. On the other hand, if you look at the actual theory that powers all the stuff, that's got a long history. It's 1985. Many of you were not doing computer science then. Some of you may not have been born then. So it's a there's a long history there. So what makes this work? What makes this work is that we have, and we may have had this for maybe the last 4 or 5 years, a significant amount of compute infrastructure that you can dedicate to these problems. Now, if you think a little bit about this, we have seen this kind of story before. We have had fast CPUs. We have always wanted to run the best, shortest path algorithm on it. But we know you can't run an algorithm on a piece of hardware until you build all the stuff in between. All the stuff in between used to be called operating systems, editors, this, that, and the other thing. So I think of all of that as system support. And that's the same thing that's playing out here, and you should not be surprised. Whether AI will be the future is less material than what do we need to do now to enable all the AI applications that are out there. And to do that, it is useful to understand what machine learning is at an abstract level, because if you're going to do systems, you need to sort of understand what is actually going on. The basic idea is that you want to calculate a complicated function from some data that you have. Now, one way you can do that is you can write this enormously complicated procedure with if, then, else's, special cases, this, that, and the other thing, lots of rules. Or you can do machine learning and infer, which is the process of learning the function f, given a large amount of data. The operative words are two: infer by learning, and the other one is large amounts of data. So you need to sort of accommodate this large amounts of data, which sort of teaches you what this function is supposed to do. You learn that function, and then in a separate step called the inferencing step, you embed that function or model, as you would call it in AI parlance, into your application so that when it's given the data input, it computes that function. It's very straightforward. So two things, training and inferencing, both of which need significant amount of systems. The driving forces, I think, if you look at machine learning is essentially two things. Okay, three things. There is plenty of hardware that is available, but we need to do some high-performance computing systems, high-performance system structure to make all those computing available. Plus, we need advances in algorithms. Even with our state-of-the-art algorithms that we have now, there is plenty of work to do in both hardware and in system software, which is why I said 2, maybe 2.5, 3. It's not that algorithms are not important, but even today, the state of the algorithms, I think, is quite far advanced. I just want to sketch some potential areas of systems research for those of you who might be interested in doing systems research. And the 3 talks that follow will highlight, in no comprehensive way, but highlight some of the work that is going on currently in systems. The first thing I said in the previous couple of slides was that we need to deal with massive amounts of data. If you have massive amounts of data, you know that it's quite a chore to store that data in a fault-tolerant fashion or in a scalable fashion, curate that data from various logs that you might be using or various data sources that are kind of raw. You need to curate that and having efficient access to the data. So that's a very central problem in dealing with the data. Now, having the data and that thing stored is not enough, right? You need to be able to run a computation on that data to learn something. Remember I told you a couple of slides ago about learning a function. So how to make efficient use of hardware to run your your training jobs on this and the inferencing jobs on the data is an important thing. And you'll hear a talk later. The first talk of the session will be talking about one particular aspect of system infrastructure called for elastic training and inferencing. A pretty big component of what makes systems research, what makes AI possible is hardware innovation. We all know how to compute on CPUs. GPUs are also fairly in the mainstream, but there is a constant quest to think of more exotic things like FPGAs and TPUs. You've heard of both of them. They are constantly in the news on how they can train or inference a model more efficiently. And the second talk in the session is going to talk about novel hardware architectures. How can you enable new hardware architectures to do these kinds of things? The last bit is systems infrastructure, system software. And my analogy, as I said earlier, is that you want to run some sort of algorithm on some piece of hardware. So there is a lot of things that go into it, even though you have the basic systems infrastructure, your hardware, your operating systems all done, you still have a lot of work to be done in compiler optimizations for turning algorithms, make algorithms faster, making models faster. It's quite an art form to do this well. Another issue is when you have these special purpose processors or special purpose devices, they don't always like to work on full 32-bit precision. Or you can do much better if we can quantize the data into fewer bits of precision. 8-bit precision is very common. People are ambitious and they want to try even lower. So dealing with quantization without losing your accuracy of the model is a very hot area, and a lot of people work on that. It's also related to the previous topic, the compiler optimizations. And another important area, which we will talk about in the session, is think about the people who have all this data and who want to learn this function. That data is very proprietary, it is very high value, and people do not want to leak it or make it available to other people. So the idea of providing anonymity due to legal requirements or security for corporate, for corporate assets is a hot topic. And how do you do inferencing and learning in the presence of encryption or obscure data is also quite a hot challenge. So think of this list as areas that you might want to do work in, and the things are in italics, the 3 talks: the resource elastic inferencing and training, the hardware architectures, and the confidential computing or secure computing. Those are the topics of the 3 talks you're going to hear. So, let me quickly introduce the top talks today. The first talk is by Muthayan Sivatanu, and I'll introduce each speaker as they come on. I'm going to do the first one now. Actually, let me just give you the whole list first, and then I'll introduce Muthayan. So the first paper is co-designed for efficient DNN training. This is a paper that has been recently published in multiple venues. This work has been published in multiple venues, and you'll hear Muthayan talk about that. The next up will be NCN, which is talking about a new machine that they're building at ETH, and Timothy is going to tell you about that. And finally, there is a talk on cryptographic techniques to give you better AI.